Okay, so this is going to be a PowerPoint about oxidation numbers. I will send you out a worksheet uh, that you can do and send back to me, and that's all we'll have it. But uh, I wanted to definitely expose you to these because this is classic chemistry. So oxidation numbers. Sorry, my cat's going crazy here. Uh, what are you doing? Okay. Uh, so uh, so oxidation numbers, and we'll go over that, what they are in a minute. But essentially, chemistry is about reduction and oxidation. Often we call this, instead of oxidation and reduction reactions, we just call them redox reactions. Okay, essentially every chemical reaction that you will come in contact with, like I said in previous videos, is a redox reaction. Before we really knew that electrons are moving around chemical reactions, like in single replacements, where we had, like in the first chemical reaction, we talked about putting a penny in the silver nitrate. What happened was the copper transferred its electrons. Its electrons got transferred to silver. Okay, and the silver became reduced, gained electrons, and became Ag and came out of solution, and the copper lost the electrons. Okay, so I did that twice. Um, and it is oxidized. Okay, so and we could actually track the electrons. Okay, so that especially in the half reactions. Um, but before we could do that, we actually would track another way of looking at oxidation reductions by looking at something called oxidation states. All right, and I talked about oxidation states when we were looking at stock ions. Okay, like iron 1, iron 2, and iron 3, and so forth. Um, so before we knew actually that electrons move around between atoms and making electrons, they knew that there was something happening. Okay, and there was and it kind of always saw it, especially it started out with oxygen, um, and then so chemists would do reactions and notice that one substance behaved like oxygen, the other one would be attacked by that oxygen, by the thing that acted like oxygen. So you would have oxygen, which is a reducer, I mean, an oxidizer, and it is reduced, usually, and when it's in most chemical reactions. And then you have the other thing that's being oxidized. It's often called the reducer because it reduces the oxygen. But oxygen isn't always the oxidizer. Okay, but it's a good way to start. I don't know exactly how we came up with oxidation states, but my guess is that they probably did something like this. They took oxygen and added to a substance and watched it react. And then they probably had scoring systems. So they put oxygen with many different elements, and they saw how those elements react with oxygen. Then they had a scoring system. So the more oxygen would attack an element, the bigger the gain in this thing called the oxidation number. So it's an empirical number that they noticed. It wasn't theory. They didn't know the structures of atoms or to come up with these. So this is original chemistry before theoretical chemistry came along. First, maybe when they put oxygen to iron, it would double or triple the quality of the reaction. And so iron would have oxidation numbers 2, plus 2, or plus 3. Okay. Then, maybe they did with copper, and they saw that copper so reduced to plus 2 and plus 1. Like I said, I'm not really sure how they came up with them. But these guys are known as oxidation states or oxidation numbers. Okay. So most elements have oxidation numbers. Some don't, especially the heavy metals. The ones after about 100 in the periodic table. You can find these oxidation numbers on the periodic table, and they're usually, so if you look at periodic table, you'll have you know, it's a square, and then you'll have the element, you'll have the atomic number up here, the average atomic weight down here, and over in the corners they'll have the oxidation numbers. And so this is empirically how they found. So what's important is about these oxidation numbers is that what we can do is we can track the oxidation numbers before and after reaction took place to see what has been oxidized and reduced. Like if you look at iron, can be +3, +2. I forget what else can be, a couple other ones as well. But maybe iron might start out as a +3 and then go to a +2. Okay, in that case, it gets less. It gets less positive, and it gets more. Less positive, more negative means it gets reduced. Okay. All right. So we'll be going over this. So let's look at this reaction, the formation of iron oxide, which is known as rust. And simply what you do is you take iron and you expose it to air, which oxygens in it. Or it could be water as well, because actually this reaction takes place better in water than the air because the oxygen actually is concentrated close to the iron, and this reaction can take place better. And so here's iron oxide. So what we want to do is add the oxidation states for each element and then figure out what is being oxidized, reduced. So how do we do this? So first, when the element is all by itself, just like Fe or O2, notice it's not a molecule. Okay, it gets an oxidation number of 0. So we put zeros here. And then what we can do is we can go to the periodic table and pick the oxidation number that's most likely to, for the element to be. And so that's bold. Okay, so if you look at iron, it has +3, +2, whatever, but the +3 is bold. So you put a +3 here, and oxygen is at -2. So, okay, so those are oxidation numbers. And then what we do is compare the oxidation numbers before and after. So iron goes from 0, oxidation number to 0, to +3. So that means it gets more positive. In a way that does that, it means it get more positive, it gets less negative. Hey, that's a good way to live, huh? If you want to get more positive about something, you get less negative. And then, and why does it get less negative? Because it lost electrons, and this means it's been oxidized. Oxygen, on the other hand, goes from 0 to -2, so it becomes more negative, loses positive, and the way it gets more negative is gain electrons, and we say that's reduced. So this is a way of finding out oxidation reduction without tracking electrons. You just look at oxidation numbers. Before we go, let's look a little bit between. There's a relationship between electrical charge and oxidation numbers that we have to be careful about. So if we were to write this with charges, it'd be Fe0, O2 0, Fe3 plus. Okay, so this is iron 3 plus and oxygen 2 minus. Right. Now the oxidation form has +3 and -2. Okay, notice they have the same numbers, but the superscripts signs are in different places. Okay, so oxidation form has it as 3 plus, and the electrical form has it as 3 plus. Okay, so they're the same but different. So why is this? Okay, again, the oxidation numbers are empirical. All right, they came first. They came before they knew charges. And what it means, the oxidation numbers mean that the Fe has been oxidized 3 times, so it has +3. While the ion form means it has a net 3 plus charge, so 3 pluses. Okay. All right, so it turns out, fortunately, that these two things are exactly the same thing. This is an empirical number that is actually backed up by a theoretical number. Right? So a lot of times, when people write, ions, they'll write Fe3 plus. Technically, that's wrong. Okay, because this is the oxidation number. Okay, the ion is sorry. This is the ionic form, and this would be the oxidation form. So if you write it like this and you say this is the ionic form, technically you're wrong. Okay, I won't make a big deal of it, but I just want to let you know there is a difference between +3 and 3 plus. Okay, so in single replacement we saw changes in charges, but we can get the exact same answers using oxidation numbers, which we'll see next. Okay, so let's look at copper plus silver nitrate. So this is one where you put penny into silver nitrate, and you make the silver and copper to nitrate. So here's the chemical reaction without the charges. And what I'm going to do is, instead of adding charges, I'm going to put the oxidation states. So element all by itself gets 0. The oxidation state of silver is +1. So you can just look at the bold oxidation number. Nitrogen is -3. Okay, oxygen is -2. And then we go over here again, silver is all by itself, 0. Copper is +2, that's the bold. And then nitrogen and oxygen are -3 and -2. So now if you look, the copper goes from 0 to +2. It means it gets more positive. That means it's lost electrons, lost negatives. And so it's oxidized. And silver goes from +1 to 0, so it gets less positive, more negative, and gains electrons. The nitrogen and oxygen don't change. And we'll talk about this later down the road. See, it's pretty simple. We don't have to go through the ionic, net ionic, half reactions, and so forth, okay? So if you want to come up with the oxidation state, often a quick and dirty way to do it is use oxidation numbers. Okay, so where does this come in handy, using oxidation numbers, okay? Because you could see that we could just use what we learned about ionic, net ionic, and so forth. One place that we can use it is for combustion reactions or other reactions that we really can't tell what's going on with the electrons. There's no moving electrons that we can tell. So we're going to look at this reaction down here in a minute. But if you look at it, this is not a charged molecule. It can't be broken up into ions. Like this cannot be broken up into carbon plus and H minus. This whole thing is a molecule that has no charge on it. Okay, no net charge. It's just a molecule where all the electrons and protons are equal. Okay, but when this guy combines with this guy, there is a switching around, moving of electrons. Okay, but you can't see it. But there is. And so what we want to do is see what gets oxidized and reduced. And the way that we're going to do that is use oxidation numbers. Okay. Just knowing these reactions, we know that oxygen is going to get reduced. We talked about that earlier. And it's going to oxidize the alkane. But by how much? And also, alkane has carbons and hydrogen. Are they both going to be affected equally? Okay, or differently? Okay. And so we're going to use oxidation numbers to help us look at this. All right, so what we're going to do is we're going to put the oxidation numbers up here. Okay, so if you go to the periodic table, you'll notice that, carbon has a +4 or -4 as a bold, and you're going to put that here, but that's probably may be right, but it may be wrong. Okay, so what we want to do is come up with a method Okay, so it's not so fast. We just can't put oxidation numbers with elements. We have to have a method to put oxidation of numbers of elements when they're in molecules. Okay, and even though I made it simple on previous example, okay, so we'll have a method to determine the oxidation numbers of elements in a molecule. And what I have here is this is, this is my invention, and there's things like out there. I call it the oxidation priority table, and you'll see how it works. Is that fluorine's at the top, oxygen's second, H, hydrogen next, elements with one oxidation number, chlorine, nitrogen, and oxygen, and here's our oxidation numbers. And we'll go over what this means. So it's, for instance, right off the bat, let's say I have hydrofluoric acid, and I want to find the oxidation number of each of these elements. Okay. You go to periodic table and you can find these numbers, but what we're going to do is come up with a method. We're going to find that we're going to have take care of fluorine first, and then we're going to figure out hydrogen. Okay, so hydrogen, because it's higher up on the table, we're going to use that guy's oxidation number, which will be -1. And then we're going to say is we don't know hydrogens, and using these two pieces of information plus another piece of information, we will figure out what the oxidation number of hydrogen is. So keep this available as we go along here. Okay, so all right, so let's go over some molecules to figure out their oxidation numbers. This is OF2. It's not, this 2 down should be down here. So that's oxygen difluoride, water, carbon dioxide, sodium chloride, nitric acid, and sulfate. And what we'll do is figure out the oxidation number of each element. And each molecule, then we'll start out with this guy right here. Right, first, you give the element of the two, so there's oxygen and fluorine, that is higher up on the table, so fluorine's higher up on the table. You give its oxidation number as -1. You give it an oxidation number. You give oxygen oxidation number of X. So you leave one unknown. Okay. Now, the other piece of information to know is the overall charge of this molecule is 0. Okay, how do you know that? Because there's no charge on it. Like sulfate over here is SO4 2-. If this had the charge on it, it'd be like OF2 3- or something. So this has no charge on it. Okay. So what this means is the total oxidation state of oxygen. Well, so the oxidation number of total oxidation state of oxygen is 1 times X, and for fluorine is 2 times -1. Okay, so oxygen has a value of 1X, and fluorine has a value of -2. Let's say, how do we find X? And this is where we use the overall charge as a value. So the sum of the oxidation numbers, or in this case 1X plus -2, has to equal the charge on the whole molecule, which is 0. So we get 1X plus -2 equals 0. And then we simply solve for X, and you can see that X equals 2. We have to give it a plus. We just can't leave this off because this has direction. It's like a vector. It has magnitude and it has direction. So X is going to equal 2 plus 2. So you're going to put down oxygen with a +2. Now, if you look at on the priority table, it has oxygen with a -2. Okay, so fluorine can mess up oxygen. Okay, in fact, fluorine is the only thing that can change the oxidation number of oxygen when it's in a molecule. So the key is whenever you feel oxidation number, find oxidation number, is to leave one of them unknown. And sometimes it actually gives you the number to expect, but not in this case. And that helps. Okay, so we're gonna be using this table in the next few. I'm not gonna carry it over the next slide, so you can maybe write it down for yourself and see what I'm doing here. So this is, let's go to water. So oxygen is higher up on the priority table, and so we give it a -2 right here, and hydrogen is lower, so we give it X. And so what we have is hydrogen is 2 times X, and hydrogen is 1 times -2, or 2. The overall charge on water is 0. So what we have is 2x plus -2 equals 0. And when you solve for x equals 1 or plus 1. So here, what you get. And notice that the oxidation number of hydrogen is what you would expect, plus 1. Okay, hydrogen almost in all cases is going to be plus 1. I've seen it sometimes as -1. Remember, these up here are not charges. Okay, so you don't crisscross charge, don't crisscross these or anything like that. So don't get messy with things. Don't try to do this and go, oh, I'm gonna bring the 2 over here, and so I have, okay, right, is that don't use these at all to figure out subscripts. Okay, these are just to see what gets oxidized and reduced. Right, carbon dioxide. All right, so you have oxygen's higher up on the table. In fact, carbon is not even on the table, so you have to figure it out. So carbon gets an X, okay, and oxygen gets -2. And so you get carbon equals 1x and oxygen equals -4, 2 times -2. The overall charge in carbon dioxide is 0. Okay, there's no, if it had a charge, like, it might be something like that, but it doesn't. Okay. So to find x, so it's going to be 1x plus -4 equals x. Equals 0. Okay, then solve for x, and you get x equals 4 or plus 4. Okay, so here's, you got C has an oxidation of +4, oxygen has +2. You'll notice on the periodic table that carbon has many oxidation states, and in fact, +4 is one of the preferred. So when you look at the oxidation numbers, when you calculate oxidation number, often go and look at the periodic table to see if indeed that is, if that number is it. If it isn't, then you may want to check your work. That's not always the case, though. All right, sodium chloride. So you notice on the priority table that sodium's not there, but it only has one oxidation state, so it's +1. And we said that anything has only one oxidation state is higher than Cl. So sodium's oxidation state is +1. You can find that from the periodic table. We give chlorine X, even though on the priority table it has it -1. We're not going to put it there because it might be different because of who it's attached to. Okay, so total oxidations are for sodium 1 times +1. So there's 1 here times +1, and chlorine is 1 times X, or 1x. Okay, so again, this molecule overall has a neutral charge. So it's going to get 1x plus 1 equals 0. Solve for x, you get -1. And chlorine is -1. And that's what you would expect, okay? But Chlorine isn't always -1. If you look at the periodic table, sometimes -3, -5, and I think it might be a plus score as well. Okay, nitric acid. So nitric acid's a little bit different because it has 3 elements. So the key here is you got to leave one unknown. All right, so which one are you going to leave unknown? Well, you can see that oxygen and hydrogen are higher than nitrogen. So you both give them their values. So oxygen is -2 and hydrogen is +1 and nitrogen is X. So here's the hydrogen, here's the nitrogen, here's the oxygen. Okay, overall this molecule has no charge on it. Okay, so one hydrogen, so there's a 1 here, a 1 here, and a 3 here. So it's 1 times +1 is +1. Nitrogen is 1 times X, or 1X, and oxygen is 3 times -2, or -6. So when you so you get +1. This should be plus X. Should be pluses in between these guys. So +1 plus 1x plus -6 equals 0. Solve for X, and you get X is equal to +5. And so nitrogen is +5. It's oxidation number 5. And if you look at that on the periodic table, that is indeed one of its main oxidation numbers. Okay, sulfate. Okay, so sulfate's a little different because the overall molecule has a charge of -2. So oxygen's higher than sulfur. In fact, sulfur's not even on the table. So we give oxygen -2 and sulfur X. Okay, so sulfur is 1 times X and oxygen is 4 times -2. Okay, not this 2 up here. Okay, all right. This is the -2 of the whole molecule. So right now we're just looking at SO4. Okay, not like the 2-. So this has X and this has a 2-. Okay, so 4, this 4 times 2- is that. Okay, now this whole thing has a, -2, that should be, sorry. This whole thing has a -2 charge. 2. Okay, so we get 1x times -x equals -2, which is the overall charge of the whole molecule. So sulfur X is +6. And if you look at the periodic table, you see it's one of the expected values of sulfur. So sulfur is +6, oxygen's -2. This whole molecule has a charge of -2. Or 2-. Okay, you can write it as -2 or 2- here. So let's go back to our combustion of propane and see if we can figure what gets oxidized and reduced. So here's our equation. And actually, we don't even need the coefficients to do these reactions to figure out what's being oxidized and reduced. So we're not gonna look at the 3 and 4 and the 5 here, and even the 1. Okay. So what you can do is just find the oxidation number of the carbon and hydrogen in the propane, and the oxidation of oxygen, and a number of oxidation number of carbon and oxygen and carbon dioxide, and this one as well. So propane, if you look at the priority table, hydrogen's higher up than carbon, so it gets +1, and carbon gets X. The total oxidation number of propane is 0. There's no charge on this guy. So we got carbon is 3x and hydrogen is 8 times +1. There's 8 and it's +1, so it has +1 and x, so 3x, and 1 times +1 is this, and so you get 3x plus 8 equals 0. And then you solve for x, and it turns out to be something weird. Okay, it's -8/3. Okay, now even though it's weird, it still tells us something. Okay, and we're going to use that. So carbon is minus 8/3 3, and hydrogen is plus 1, and there's 8 of them. Oxidation state of O2 is 0, so you write as O2 is 0, since it's all by itself. Carbon dioxide we did already, and water we did already. Now what we can do is compare each element at the beginning and end of their oxidation numbers to see what happens to them. So carbon goes from minus 8/3 to plus 4. So that number increases. That means it gets more positive. And the way it gets more positive is because it became less negative. And the way it became less negative is lose electrons. Okay, and it doesn't really lose electrons, but the electrons kind of move in a way that they're not as exposed or not shared equally as much anymore. But really, we'll just say they're lost. Okay, hydrogen goes from plus 1 to plus 1. Okay, it's plus 1 here and it's plus 1 in water. So nothing, so it kind of acts like spectator. And oxygen goes from having no charge here to having over on this side a minus 2 on both the carbon dioxide and the water. Okay, so its oxidation number, so it does that twice. Okay, so its oxidation number decreases. That means it gets more negative, and to get more negative it gains electrons, and we call that reduced. So we, from this analysis of oxidation numbers, we can figure out that oxygen gets reduced, the carbon gets oxidized, and the hydrogen, we say nothing happens. And that's an important concept in all of what we're talking about. And again, essentially the main, what makes chemistry in our course is oxidation reduction. Actually, to figure what is being oxidized, you don't have to balance equations. I told you that, but it's you don't have to have the coefficients, but it's often it's preferred to have a balanced equation. But so what I'm going to do is I have this equation here that's not balanced. All right, you can see there's 2 hydrogens over here and there's only 1 here. We're not going to worry about that. Okay, all we want to do is look at the oxidation numbers. So what we're going to do is find the oxidation number for each element, the ON. So Cr2O7 2 minus has overall charge of 2 minus. Okay, that's what this guy up here means. Oxygen's higher than chromium. Chromium isn't even on the chart, so oxygen gets a minus 2 and chromium gets X. So we find what we need to do. So chromium is 2 times X, and oxygen is 7 times minus 2, minus 14. So we get 2x plus minus 14 has to equal minus 2, and solve for x, you get plus 6. So chromium is plus 6, oxygen is minus 2. Okay, hydroxide. The overall charge is 1 minus, or minus 1. Oxygen's higher than oxygen, so oxygen is going to be minus 2 and hydrogen is going to be X. So oxygen is, there's 1 of them, so it's 1 times minus 2, and hydrogen is 1 times X. So we get minus 2 plus X equals minus 1, and so X equals plus 1 for hydrogen. And here is how you write it out. Okay, CrO42 minus, similar as what we did up here. Okay, oxygen again is higher than chromium, so you get minus 2 and chromium X. There are 4 oxygens times minus 2, so minus X. Chromium, there's only 1, so it's minus X. Minus 8 plus 1x equals minus 2. Okay, when you do the math, so you add 8 to both sides, you get plus 6. And again, it looks like chromium is plus 6. And so, there you go. We know water already. And let's look to change the oxidation state. So oxygen goes from -2 to -2, so nothing changes. Chromium goes from +6 to +6, nothing changes. And hydrogen also goes from +1 to +1. What I mean also, it doesn't change. So it looks like nothing is being oxidized and reduced here. And the reason for that is we left something out. There is, for doing these types of reactions, and we may get into those, is that you have to add acid and base to it. And we cover that more in Chem 122. Okay. So even though it looks like nothing being oxidation and reduced, there actually is, but not from what you see here. Okay, this one right here, NH4 and NO2 yields N2 plus H2O. So this isn't balanced as well. Okay, it doesn't matter. We can still find out what's being oxidized or reduced. Now this one's a little odd. Notices that nitrogen is in two places on the reactant side. Now why don't we just write as N2, okay, H4, O2. And the reason why we do that is because these are two different substances. All right. This is ammonium and this is nitrite. And they behave differently when this reaction takes place. Okay. So we have to treat the nitrogens different. So what we do is, so this is ammonium nitrite. Okay, it decomposes into nitrogen gas and water. So if you have polyatomics together and they have, like in this case, you have to treat them separately. So we have NH4, which is, this really is NH4 plus ammonium. H is higher on the priority table, so it gets +1. Nitrogen gets X. And the overall charge on this molecule is +1. So we get N is 1x and hydrogen is +4. So we get 1x plus 4 equals +1. And solve for X, it's -3. So nitrogen is, so the nitrogen in ammonia has a -3. Now nitrite, overall charge of -1. Oxygen is higher on the table again than nitrogen. So it gets -2. Nitrogen X. The overall charge is -1. So nitrogen is 1x and oxygen is -4. So you get 1x plus -4 equals -1. Solve for X, it's +3 now. So the nitrogen in nitrite has an oxidation number of +3. All right. Now we wouldn't have known that if we put it all as one substance. Okay. So then the nitrogen is all by itself, so it gets a oxidation number 0, and we know water. So let's find a change in oxidation numbers. So nitrogen on the product is both 0 for the ammonium nitrate. So the ammonium goes from -3 to 0. That means it becomes more positive. It loses, the way it does that is lose negative, so it's being oxidized. The nitrite on the other hand goes from +3 to 0. Okay, so it becomes less positive, which means it becomes more negative, and it's reduced. And the oxygen and hydrogen have no change. Okay, finally, let's go back and look at copper plus silver nitrate example. So this is what we started out with. Now we can do a little trick with this. Is that whenever you have a polyatomic ion, right here, nitrate, you notice it doesn't change. Okay, so nothing's going to happen to either one to the nitrogen and oxygen. And so what you can do is you can cancel those guys out. Okay, so the polyatomics, if they just move back and forth from reactant product side, you can essentially just write them out, cancel them out, and then you could write it out just that you can write out the give the oxidation numbers for the things that for the metals. So oxygen is for copper is 0. Silver, because it was with the nitrate, had a +1. So okay, so even though that we took the nitrate out, it made this have a +1. So when you first write it out like this, and notice this is that then silver is not all by itself, okay? And so it does have an oxidation number that's determined by what it's attached to. In this case, the silver has 0 because it's all by itself. And again, copper is 2 plus. Okay, it's not 0 because it's attached to something. Okay, and all right, and you know, in this case, we have this +2. So essentially, this is the net ionic equation. So if the polyatomic ions are unchanged to reaction, you're going to ignore them and figure an oxidation number. So you see that the copper goes from 0 to +2, so it's being oxidized. And the silver is going from +1 to 0. The number is being reduced, which means it's getting more negative, gaining electrons, and so silver's that. So there is the little lecture on oxidation numbers, and there will be a worksheet that you'll have to write, and that'll be the last thing we do with reactions in terms of what reactions are and study them for right now. Okay.